Hello, myself Pushkar Sanjay Maske. My topic is digital stopwatch implementation. Overview: a digital stopwatch measures elapsed time using a clock signal. In this project, we use three main components: clock divider to slow down the clock frequency, counters to keep track of a time unit like a millisecond, seconds, and minute. Control logic to manage the starting, stopping, and resetting the stopwatch. Clock dividers since Xilinx FPGA operate at a very high frequency, typically 100 MHz. We need a clock divider to bring this down to 1 Hz, which we can use to measure seconds. The formula for the clock divider is a simple. We divide the input frequency by desired frequency. So to go from 0 MHz to 1 Hz, we divide by 100 million. Counter design: the stopwatch uses three counters. The millisecond counter from 0 to 999. The counter second counter from 0 to 59. The minute counter from 0 to 59. These counters work together to measure the time accurately. In control logic, the control logic include three main functions: start, stop, reset. Start: this activates the counter. Stop: this pauses the counter. Reset: this set everything back to zero. The logic is based on a finite state machine, which three states ideally running and pause. Xilinx circuit diagram. Here a basic diagram of the circuit. It include clock divider, the counter, and the control the logic with the final output shown on a display, like a 7-segment display or a LED. The test bench simulate the behavioral of the stopwatch, testing various functions like a stop, stop, and start, stop, and reset. It uses the simulate clock signal to observe if the stop works as expected. In simulation results, here are the results from our simulation. When we press start, the counter increment. On a stop, the stopwatch pauses, and pressing the reset bring everything back to zero. Mm, Conclusion: to conclude, very successfully implemented a digital stopwatch by using a clock divider and counter to track the time. The control logic manages start, stop, and reset the function, and we verified everything through a simulation. In the future, we could add a more precise the time tracking like a microsecond or a microsecond or implement it in real-time hardware. Thank you. I will explain a visual code that simulates a stopwatch. This purpose of this code is to count the second and minute, allowing the user to start, stop, and reset the timer. Let's break down how it works step by step. Code components, libraries, and entity. This code begins by including a standard library that help manage logic, signal, and operations. The entity name stopwatch has an input and output for a CLK, the clock, and rest, start, and stop control. It also output called a second and minute, which display the current time in second and minute. Second architecture, internal signals. Inside the architecture server, inside the architecture servers, signal are defined. Clock driver divider divides down the input clock to slower 1 second impulse. 1 second clock. This 1 Hz signal will toggle every second. Second counter and minute counter. This keep track of seconds and minutes respectively. And running signal, a flag that indicate whether the stopwatch is counting. Clock divider. The input clock signal is divided to create a 1 Hz pulse. So our second counter increment once per second. This is done by checking if the clock divider Clock, this is done by checking if the clock divider reaches a count of 100 million cycle, assuming a 100 megahertz clock. When it does, it toggles the 1 second clock signal and reset the clock divider to zero. Control logic start and stop. Another process check the start and stop the input. If the start the signal is high, the running flag is set to 1 allowing counting to begin. If the stop signal is the high, the running flag is set to 0, pause the counting. Second and minute counters. Second counter. This process increments second counter every time. 1 second clock has a rising edge, but only if the stopwatch is running. If the second counter reaches 59 seconds, it reset to 0 and roll the over. Minute counter. When the second counter reset from 59, the minute counter increment if it reaches 59 minute also reset to 0. Assign output. The value of the second counter and the minute counter are assigned to outputs and second minutes. Mm, This is the output of the code. This diagram represents a simple digit stopwatch module showing the inputs on the left and output of the right. Input on the left side clock. This is the clock signal which keeps the stopwatch running by the providing regular time interval reset, and this output reset the stopwatch when activated. It set both the second minute and back to 0. Start the this input start the stopwatch, allowing it to count up. Stop This input stopwatch, pausing the counting. Outputs minutes, and this shows the number of a minute counted by the counted count in the 5 minute means it's a 6-bit signal capable of representing value from 0 to 59 minutes. Second, the display number of a second counted also as a 6-bit signal, allowing it to count from 0 to 59 seconds. How it works: when you activate the start input, the stopwatch begins a counting second and minute. The stop input the pauses the counting, while the reset input set everything back to 0. The outputs minute and the second show the current count in binary format. This visual code is the is a test bench designed to simulate and the stage bench functionality of a digital stopwatch module. Let's go through the code step by step in simple terms. Overview. This purpose of this code is to test the stopwatch behavior in different resetting, starting, stopping, and restarting. This help ensure the stopwatch functions as expected. Structure of the code: a library entity. This code uses the IEEE library to work with the standard logic data type. This entity counter underscore TB underscore VHD define this as a test bench with a no input or output ports, since it only simulates the internal behavior. Component declaration for the unit under test. This component stopwatch is a declare matching and the design we want to test. This component watches. The component has a 4 input signal: clock, reset, start, stop, and 2 output signal: second, minute. Signal and clocks setup. Signal like clock, reset, start, and stop are defined to control the stopwatch. The clock period is to set 10 ns simulating a 100 megahertz clock. We create an instant of the stopwatch module, linking the single defined in the stage bench to the port of the stopwatch. Clock generation process. This clock process create a clock single byte by the clock signal every half of the clock period 5 ns, simulating a 100 megahertz clock for the stopwatch test sequence. This test the TV process runs the actual test sequence, resetting it start by the activating the reset signal, setting the stopwatch to 0, starting the stopwatch. After the releasing the reset, it activates start, allowing the stopwatch to begin counting, stopping after a 10 simulate second. It state stop to pause the stopwatch, resetting. mm, Reset again, resetting it then the clear stop after 5 seconds to resume counting. Reset again, finally it reset the stopwatch once more to observe the reset behavior. After all action, this code reaches the end of the test sequence, completing the simulation. This is the output of this code. This top section is clock reset start and stop. These lines represent a control of the signal clock, and this is a regular respective signal that set the timing for the circuit reset. This signal is used to reset the circuit. It goes high at the start, which likely reset the everything. Start and stop, these are a control signal used to start or stop the circuit. Start goes high briefly, which might indicate the beginning of the some process. Second and minute. This line represent a counter for the second and minutes. Second, and this is a 6-bit counter for a second, meaning it can count up to 63 minutes. This is also 6-bit counter for a minute. At the moment of the shown 100 ns, both the counter for the second or the minute are still at a 0, as indicated by the gray bar with the number 0. This suggests the counter has not start counting it or are waiting for the specific trigger. Thank you.